Welcome back, focused learners, to another explainer. Today, we're diving straight into one of the absolute most crucial characterization techniques used in perovskite solar cell research, X-ray diffraction, or XRD. You see, if you want to understand how a perovskite solar cell works, how it degrades, or how to improve it, you have to look at its structural fingerprint. And XRD, it's the ultimate tool for reading that fingerprint. It gives us direct, undeniable information about the crystal structure, phase composition, crystallinity, and even the structural degradation of the perovskite absorber.
Here's our roadmap for today. We're going to start with Section 1, the basics of XRD. Then move to identifying phases and impurities in Section 2, tackle crystal size and microstrain in 3, and explore tracking degradation and dynamics in 4. Then, we'll synthesize it all in a step-by-step pattern analysis, and finally, get a much-needed reality check on limitations and common mistakes. Okay, let's dive into this highly structured micro-to-macro journey through the material.
Section 1. The basics of XRD, the structural fingerprint. You know, everything we do in perovskite research, literally every single tweak to the chemistry or change in processing, ultimately alters the fundamental physics of the crystal lattice. And that is exactly where we have to start. At its core, X-ray diffraction is a non-destructive technique. It's used to figure out the exact arrangement of atoms inside a crystalline material. When X-rays interact with a material like a perovskite film, they're scattered by the atoms. And at very specific angles, those scattered X-rays interfere constructively, which gives us these distinct diffraction peaks. Because any change in composition, strain, or defects physically alters that crystal lattice, it consequently alters this entire XRD fingerprint.
The math behind all this is beautifully captured by Bragg's law. N lambda equals 2d sine theta. Let's break that down carefully because it's important. Here, lambda is your X-ray wavelength. Most laboratory instruments use copper K-alpha radiation, which sits at about 1.5406 angstroms. That d right there is the crucial spacing between the crystal planes, and theta is the Bragg angle. So by simply measuring that diffraction angle, 2 theta, we can directly determine the interplanar spacing, d. It's the foundational mathematical link between the diffraction pattern we capture on the screen and the physical reality of the perovskite crystal structure.
Moving to Section 2, identifying phases and impurities, the first glance.
Now that we've got Bragg's law in our toolkit, we can apply it to real films. The first and most vital step is identifying what actually formed on your substrate. Let's say you fabricate an PbI₂ film. You obviously want that desirable black perovskite phase. By comparing your XRD pattern to a known reference, you look for those characteristic reflections. But you also have to be on the lookout for impurities and residuals. For example, spotting the delta phase or residual lead iodide, PbI₂. Now here's where reading this fingerprint gets a little nuanced. Excessive PbI₂ means incomplete conversion, which definitely hurts performance. But a tiny, strictly controlled amount of PbI₂, that might actually passivate defects and improve crystallization. So it's not just about what is there, but exactly how much is there.
Section 3. Crystal size and microstrain, the deep analysis.
We've looked at what phases are present, but what about the physical condition of those crystals? Now, what's really interesting about this next part is a question we absolutely have to pose. Is a broader peak always a smaller crystal? It is incredibly tempting to look at a broad XRD peak and instantly conclude, yep, I have small crystallites. But that is fundamentally incomplete. Sure, peak broadening can originate from small crystallite size, but it can also come from microstrain, structural disorder, overlapping phases, or honestly, even just instrumental broadening.
To figure out what's actually going on with a broadened peak, we gotta look at the math again. The Schreier equation is a fantastic starting point, but it primarily pins broadening on coherent crystallite size. If strain is significant in your film, the Schreier size can be totally misleading, and that is where Williamson-Hall analysis steps in. By graphing beta cosine theta on the y-axis against 4 sine theta on the x-axis, this method lets us calculate the slope and intercept to actually separate the contributions of crystallite size from the microstrain. It gives us a much more accurate, detailed picture of the internal physical distortions happening inside the crystal.
Speaking of internal distortions, let's talk about strain. Perovskites are mechanically soft. They can easily develop residual strain during film formation, cooling, or thermal annealing. If the lattice experiences tensile strain, it expands, d increases, and that diffraction peak shifts over to a lower 2 theta angle. Conversely, if it experiences compressive strain, the lattice contracts, d decreases, and the peak shifts to a higher 2 theta. This is absolutely vital to track, because residual strain directly impacts non-radiative recombination and the long-term stability of the solar cell. But hey, it gets even more complex. Thin film perovskites don't just experience uniform strain, they can actually have different strain states in different directions because of mechanical coupling with the substrate. You might literally have tensile strain parallel to the substrate and compressive strain perpendicular to it. This is exactly why researchers use out-of-plane XRD to measure information perpendicular to the substrate and in-plane XRD to measure planes parallel to it. Combining both is what gives you the true anisotropic strain state of the material.
Section 4. Tracking degradation and dynamics. Operational analysis. So far, we've really only looked at static films, but tracking dynamic changes, like moisture degradation over a 500-hour timeline, brilliantly illustrates how XRD acts almost like a time-lapse camera for crystal structure. You start with a fresh film at 0 hours. By 50 hours, you might start seeing some early structural changes. Then, by 100 hours, new decomposition peaks literally emerge right on the scan. And by 500 hours, you're seeing significant structural degradation as those primary perovskite peaks disappear entirely.
Another massive dynamic challenge, particularly for wide bandgap tandem solar cells, is light-induced phase segregation. Picture this. You start with a nice, uniform mixed halide perovskite, where iodide and bromide are perfectly evenly distributed. But under illumination, they segregate. And because different compositions have different lattice parameters, XRD tracks this perfectly in real time. That initial single diffraction peak broadens out and then literally splits right before your eyes into multiple components representing iodide-rich and bromide-rich regions. It's a fascinating, dynamic process to observe.
Now, what if you're dealing with extremely thin films or trying to catch super fast crystallization kinetics? Well, conventional laboratory XRD has some limits there, moderate thin film sensitivity, and it really struggles with buried interfaces. Enter GI wax, or grazing incidence wide-angle X-ray scattering. By using a highly intense synchrotron source and hitting the sample at a tiny grazing angle, it essentially just skims the surface. This provides incredibly high thin film sensitivity and excellent resolution for texture and buried interfaces that a standard lab setup just cannot see.
Section 5. Step-by-step pattern analysis. The playbook.
We've covered a tremendous amount of theory today. Let's move to the playbook and see how this builds into a rigorous, foolproof workflow for the next time you're staring at raw diffraction data. Step 1. Identify your substrate peaks first. You definitely don't want to mistake an ITO peak for a brand new phase. Step 2. Confirm your desired perovskite phase and any secondary phases like PbI₂. Step 3. Carefully examine your peak positions for any shifts that might point to strain or compositional changes. Step 4. Analyze the full width at half maximum, or FWHM, to evaluate size and strain. Step 5. Check those relative intensities to see if your crystals have a preferred orientation. And finally, Step 6. Correlate this structural data with your optical and electrical data, like JV and PL measurements. Make sure no data point is missed.
Section 6. Limitations and common mistakes. The reality check.
Before we wrap up, we need to adopt a bit of a cautionary tone. Because XRD is so incredibly powerful, it's also incredibly easy to overinterpret the data. So let's rapid-fire bust some common myths right now. First, an intense, higher peak does not automatically mean a better or more crystalline film. It could just mean you have a thicker film or one with preferred orientation. Second, peak shifts are not strictly proof of strain. Composition changes, especially in mixed halides, will also shift your peaks. Third, please don't blindly use the Scher equation if microstrain is present. Fourth, and this is a huge one, do not call coherent crystallite size grain size. XRD measures coherent crystalline domains. SEM measures morphological grains. A single 500 nanometer SEM grain might actually contain several 100 nanometer XRD domains. They are absolutely not the same thing. And finally, don't ignore overlapping mixed phases that might just look like a single broad peak.
So the crucial point here is that XRD cannot tell you everything. It gives you incredible essential data on long-range crystalline structure, phase, and strain. But it will not tell you your exact defect density, your carrier lifetime, or your actual device efficiency. It is just one part, albeit a massive part, of a multimodal characterization strategy. You absolutely must pair XRD with SEM for morphology, photoluminescence for carrier recombination, XPS for chemical states, and JV testing for actual device performance to really get the complete story.
So, we leave you with this final thought. We've seen how XRD decodes the structural fingerprint of perovskites, revealing the subtle interplay of strain, phase segregation, and degradation. But since XRD only tells us part of the story, what techniques will you combine to build your ultimate multimodal characterization strategy? True breakthroughs in perovskite stability rely on synthesizing all these data points together. Thanks for joining us for this deep dive into XRD. Focus learners. Keep analyzing, and we'll see you in the next explainer.